Okay, thank you very much. So I am going in this lecture. I'm going to talk about supernovae from binary and pair instability supernovae. So these two are kind of different topics. So it's divided into half and half. And of course, we don't have much time, so I will go quickly over through those topics, especially supernovae from binary. This is very huge topic, but I will show you some idea, and I'm not going to much detail, but I hope you can get some ideas. So let's start from supernovae from binary. There was a question about how much fraction of stars in binary system, and actually we have some observational constraint from in nowadays, and more than, at least for OB stars, massive stars, more than 70% of them are in binary system, which can affect in which their evolution can be affected before the explosion. So there can some of them can be. I will explain in more detail. Some stars, the envelope may be stripped because of the presence of the companion star. Some of them may merge, and some of them have a different effect. So very briefly, I will discuss three different types of the effect from the binary evolution. One is mass stripping. If there's another star next to the massive stars, then the mass can be stripped by this companion. Then, of course, if there's two stars, they may merge at some point. That can result in a different kind of supernovae. And also, as I explained in the lecture in the morning, rotation of stars can have a strong effect on the evolution of the stars. And because if there's a companion star, there will be a binary. The orbital energy that can make the star rotate rapidly because of the tidal interaction. So binary system can also affect the rotation in the stars, and that can lead to a different kind of evolution. So I will overview these three different possible effects in the binary system. And this was covered in the first lecture, and so this is the HR diagram, and the stars start to evolve from this end, and then low mass stars evolves to red supergiant, so it expands and then die in the other end. And as I explained, if the mass is large enough, then stars can have a large mass loss, and then after expanding, these stars can lose all the hydrogen-rich envelope and then explode as a Wolf-Rayet star, so without any hydrogen. So this was again shown in the first lectures. This is the initial mass of the stars, and this is the final mass. And if there's no mass loss, then this should just correlate. And because of the mass loss, so up to like 25 solar masses, they have some hydrogen left, even at that time of explosion, but the mass will be reduced. And from around 25 solar masses, then you start to lose all the hydrogen, and then you only have helium and these heavier elements in the star, and they become type 1b3 supernova, which was explained as well in the previous lectures. So these mass loss, if you only have a single star progenitor, is caused by the radiation-driven wind. But if there's that's why you only have a hydrogen-free star from the very massive stars, because they are bright and has more radiation to push the outer layers. But if there's a binary system, that can lead to a more complicated way to lose the mass. So this is a kind of gravitational potential of a system if there's two stars. So if there's two stars, roughly speaking, if you cut in this way, you have so if there's nothing, then potential is just like this. But if there's two stars, as you see, this maybe will. If there's two stars, you have something like, so this is just we cut it. This is the gravitational potential, and I cut it in this way. And then of course the stellar envelope has some radius. Stars has some radius, and let's say more massive stars should evolve faster. So if let's say the stellar surface is here, then from some moment the star can expand, as we saw in the first stage. So this can basically start to fill out this potential, and then some moment you start to fill this inner layer, and then mass start to be transferred from from this star to the other one. That can, so this star can take the mass from the other star, and that will lead to the extra mass loss from the which didn't happen in the original single star system. So that kind of mass flow from this binary system, these are called Roche lobe, and the mass can be went away from this Roche lobe. So this is kind of schematic picture of binary stellar evolution. And let's say this is more, so there's a binary system, and one star is more massive, and there's the other star, and more massive star evolve faster and expands early, and then fills this Roche lobe, and the mass can be transferred to the other stars. That will lead to the mass stripping. So this star is just expanding, but because of this existence of the other star, the mass is just lost from this system. And in the end, of course, you stop this, as long as this star has hydrogen-rich envelope, this star can try to expand, and this star can keep stripping the mass. And then at some point, of course, this star will lose all the hydrogen, and then this star can no longer expand. So then this star will have a lot of mass from the other system, but this star only has helium core. And then this helium star, of course, can evolve as it evolve, and then this will end up with a supernova explosion if it's massive enough. So how this will change our picture? So this is the simple HR diagram for single stars, and the stars will die in this region. So lower mass star will end up with red supergiants, and they will die in this region. And if the mass is larger, then they will die in this region as a Wolf-Rayet star. But if there's a binary interaction, then that means these stars, which were not supposed to expected to explode as a Wolf-Rayet star without hydrogen, if there's a star next to them, then this expansion will lead to the mass stripping, and some of them can explode as the Wolf-Rayet star. So this region, this is the result of binary stellar evolution, and some examples are shown. Of course, some progenitor can still explode a red supergiant, and massive star will go to Wolf-Rayet star, but some low mass star which were not type 1bc supernova progenitor can go to this region. They can explode as Wolf-Rayet star without hydrogen, and also some of them may not get they will not take rid of all the hydrogen, but some small amount of hydrogen, like 0.1 solar mass of hydrogen, may be remained. And in that case, the star will end up in this region, which is called yellow supergiants. And these progenitor can be also naturally explained by the binary evolution. So as Masomi explained in the previous lecture, now we have several progenitor detections. So if we go back to if we happen to have an image before the explosion at the supernova site, we can directly observe which stars has exploded, and we can plot these stars on this diagram. This is some results. So of course, we have many red supergiants exploding, but we do know some stars in these regions also are exploding, and those cannot be explained by the single star evolution. But if we take into account the binary star evolution, these stars can be also naturally explained to be supernova progenitor. So these are all kind of theory. If the stars, these of course suggest there should be binary star evolution, but direct way is to confirm this is again to observe the star which is which is in binary systems. So this is one example, and this is supernova exploded in 2011, and at the location of this supernova, there happened to be an image from Hubble Space Telescope, and people went back to the previous image and found a star in the location of supernova, and then they could plot. So this is the star which was exploded. So this star disappeared after the explosion, so we know this was the progenitor. And as I explained, so this must correspond to like somewhere there, I believe. Yes, well, it's maybe somewhere there. So this is again the HR diagram, and these are massive single star evolution, and they won't die here, but this was the star which was exploded. And then, so this is some detailed binary star evolution. This is evolution of I forgot the masses, but like let's say 15 solar mass or something like that. And then, so this at first, of course, the star will evolve as so even if there's two stars, each individual star evolve as a single star, and then after expansion, this will, so if there's nothing, then it just goes to red supergiants. But if there's a companion star which is shown in blue, this companion star will take the mass, and then it shows more complicated evolution than the single star evolutions. So in this particular model, they predict this star should end up with exploding here, and that's exactly so this red region is where they found this star. So this region, this area region is written here. So this can explain the progenitor exploded as 2011 DH. And then, of course, what the strong prediction is there should be this companion star there. And then what we can do is wait for a while and then look again to that position to see if this star is really there or not. So that's what they actually did, and about 4 years later they looked into the same position. So there was an image before the explosion, and then supernova happened, and then after a while they observed the same position. So and they found something at the position. This is also Hubble Space Telescope image in different bands, and they found some stars are remaining at the supernova position. So they found a star in, so this is again HR diagram, and they found a star here, and these blue positions are the expected brightness of the companion star, which should have remained there. And there's some parameter some uncertain parameter to in the binary evolution, which I am not going to into detail, but there's several, these positions can be predicted, and some model with some parameters are really predicting to companion star to be there, and so this was really wonderful match between theory and what's observed. So that was the kind of direct confirmation of star which was exploded as yellow supergiant, so with some little hydrogen. So usually if these stars explode as a single star, then it should have like tens of solar masses of hydrogen-rich envelope, but it only had a 0.1 solar masses of hydrogen-rich envelope, and that was stripped by the because of the existence of companion star, which was confirmed by observation of this companion star as well. Of course, this case was very lucky, and we cannot do this kind of study for all the type 1b supernova or the supernova to see if there's a binary star or not. And so what we can do instead is to get some idea of, let's say, ejecta mass from the stripped envelope supernovae, and this is again the prediction from the single star evolution. And what they predict is, so to get for the mass of the hydrogen poor supernovae should be from these massive stars. These are the final mass the single stellar evolution predict. So these must be, so let's say these 7, 8 solar masses, and nothing is like very low 3 or something. And of course, this is the total mass, and then there should be some compact remnant remaining. So you can, so from let's say 8, the 8 is the minimum mass, and you can subtract like 1.5 or so, and so that means the ejecta mass should be more than like 5 solar masses for the single stars. But from binary stellar evolution, you can, because of the existence of extra stripping star, you can basically get rid of these mass down to you can take those masses and have let's say 1 solar mass progenitor as well. So much smaller ejecta is possible from the binary stellar evolution. And this was already covered by the previous lecture, and so one way to estimate the mass from the supernova progenitor is to use these light curves, and as we have already seen, this time scale is in this way, and then if we have a spectrum, then we can also get the information on velocity, and that will lead to you the mass and the energy estimate from the supernova observations. And as we have already seen, this is so by doing this exercise for many supernovae, we can get the mass probability distribution for the ejecta mass for stripped envelope supernova, and these are all coming from the supernova with very small amount of hydrogen, and the most of the masses, ejecta mass, is estimated to be, let's say, peaking at around 3 solar masses or so. And as was explained, so single star evolution, they predict, let's say, more than 5 solar masses of star. Ejecta is expected from single star evolution. So if they are dominated by the mass loss, if the major mechanism to lose hydrogen-rich envelope is stellar wind from massive stars, then we expect to have the ejecta mass peaking around there, which we don't observe. And of course, even if you have binary stellar evolution, if the initial mass is large, then you still get a large core. So even if from the binary stellar evolution, they predict relatively massive core, and we don't see them as well. And the best model which can explain these distributions, binary stripping from relatively low mass progenitors, which if there's no companion star, they will explode as red supergiant without much mass loss. But if there's a binary, you can have a lot of mass stripping, which can lead to these stripped envelope supernovae. So these are general idea, and you may think there's no massive star is exploding as Wolf-Rayet star, and all the type 1 BC maybe from binary and so on. But of course, we have some cases probably they are from massive single stars. One example. So I'm talking about binary system, and you may sound like binary can do everything, and everything may be binary, especially stripped envelope supernova. But we also have some cases. So the reason, this is the right curve for this particular type 1c supernova, which has a very broad right curve. And these other type 1bc supernova, and so type 1bc supernova rise in like 20 days or so, and that led to the small mass estimate. So usually they rise in 20 days or so, but some cases we know. So in this case, it takes like 30 days or 40 days to reach the maximum, and then decays very slowly. And if we do these exercise, in this case we get the ejecta mass of 10 solar masses or so. So we do also find these massive Wolf-Rayet star explosion, which should be coming from from relatively massive star. Of course, it's hard to distinguish if they in binary or they are really single, but there's some supernovae which you can explain without invoking binary stellar evolution as well. And another argument against single star evolution was this non-detection of the type 1bc supernova progenitor, and this was also explained by Masaomi. And so these are upper limits for the Wolf-Rayet star, and many Wolf-Rayet stars observed to be as bright as these detection limits. So the one argument was that it's very unlikely to miss all these massive Wolf-Rayet stars if these are coming from the massive Wolf-Rayet stars, as we observe in this case it's LMC. But what this argument is probably missing is that this is one example of evolution of single Wolf-Rayet stars, and this is evolution from some moment, and then what it does is, as the Wolf-Rayet star evolves, they go hotter and hotter, and they explode in this end, which is extremely hot. And in the progenitor detection, when we try to find the progenitors of supernova exploded and look for the image before the explosion, we use Hubble Space Telescope, and they are optical telescope, and usually in many cases they use kind of visual band, V band, so 5,000 angstrom or around there. And because these Wolf-Rayet stars should evolve as more redder and redder, this means if you're observing in optical, it should be getting fainter and fainter. So in the end, the supernova, when Wolf-Rayet star massive Wolf-Rayet star explodes, they should be extremely faint in optical, and they should be observed as like WO stars. And they are comparing these many different kinds of Wolf-Rayet stars, but they should evolve to this way as they get closer to the time of explosion. So they may not be a direct progenitor of type 1b/c supernova, and only this column needs to be compared to these progenitor limits. And then in that sense, in that case, if that's the case, we don't have much Wolf-Rayet star as bright as what we have constrained in optical, because they get much bluer and they are really bright in ultraviolet, but not in optical. So that's still one way to kind of save the single star evolution. So binary star evolution is really important, and they may be explaining a large fraction of Wolf-Rayet star supernovae from Wolf-Rayet stars, but still the single star evolution, that is wind mass loss, should be still playing some roles, and we shouldn't throw away this single star idea. And so I showed this part, and this was like supernova, stripped envelope supernova, and that was that ejects one solar masses of ejecta, and that was like normal type 1b/c supernova. And so that's the supernova commonly observed. But if after this explosion, if neutron star remains in this system, it will be more interesting stuff can happen, and that's what we call ultra stripping. So this can continue to, so this, after this explosion, this star will expand, and then some mass will accrete to this neutron star, and that can be observed as high mass X-ray binaries. Then as it expands, then this neutron star can, so as this star expands, then this neutron star may be taken, it will be in this envelope of the second star. And if there's some neutron star or some stars in the envelope, of course, this is rotating, and that can, you can imagine, so this can lead to some mass ejection, or this extra energy inside can get rid of this high envelope. And this, actually this process is very uncertain, but we imagine these hydrogen-rich envelopes should be ejected because of the existence of the star in the envelope. And then in the end, again, what happened before, there will be a helium star. So these envelopes will be all taken away, and then there will be neutron star companion. And then what happens is that then as this helium star evolves, because again, as I explained in the first lecture, if in the end, at some moment, this helium star will start shell burning after losing all the helium at the center of the star, and then this some small amount of envelope can expand. And if there's expansion, then you can have again some mass stripping from the this neutron star if they are close enough. And then so there will be some extra mass stripping, and that can lead. And then at some moment this star will explode. And actually, this second supernova, they can only, so because of this extra mass stripping, they will only have like ejecta mass will be like only 0.1 solar masses, so about 1 order of magnitude lower envelope can be achieved in this way. So in a usual stellar evolution, binary evolution, you get 1 solar masses, but if it continues, we can get like 1 order of less ejecta mass as a second supernova. And why we care about this? So of course, this is apparently very rare way of getting supernova, but this evolutionary path is very important because this explosion, so yeah, we call this supernova ultra strip supernova because the stripping is much way larger than the normal way. And what can remain there is the double neutron star system. So if, let's say, if there's a neutron star and the normal star system, and this normal star just explodes with like 10 solar masses of ejecta, then this system will dynamically unstable, because if the binary system loses more than half of the mass at one time, then this binary system will be dynamically unstable, and then you cannot keep the neutron star binary system as we observe in gravitational wave observatory. So to keep binary system even after the supernova explosion, this explosion shouldn't have much ejecta. So in this way, if this you can avoid having a lot of mass ejecta, so you can easily keep this neutron star binary system, and with this kind of ultra strip supernova can lead to the binary neutron star system, which can merge in Hubble time, or even faster, and that may be a major path to get the neutron star binary system, which we observe as a gravitational waves. So, and another important, so this is kind of simulation, numerical simulation of neutrino-driven explosion for ultra-stripped supernovae, and this is with different core mass, and what people get. So this is one example of a result of the supernova explosion simulation, and this is from another group, but they get basically similar results. And what's important is they predict like 10 to the 50, so the explosion energy is smaller than the usual supernovae, and the ejecta mass is 0.1 or 0. A few. So this is the expected ejecta mass, and this is normalized in 0.1. And what is also important is they predict very small neutron star kick, and that's again important to keep the binary system. If this supernova has huge kick, then of course that can also lead to the dynamical unstable. That large kick will just destroy this binary system, and that won't lead to the binary neutron star merger. But because this kick is quite small, you can keep this binary system very easy. So ejecta mass is small and the kick is small, so this system is really ideal to make the double neutron star systems. And of course, question is if we observe such supernovae or not. And now we have one good candidate for such supernova. So this is the light curve again, light curve of this particular type 1b supernova. And this is spectra they took around the peak. And as you can see, this rise time is like so in 5 days or 7 or something like that. And we saw previously the rise time of type 1bc supernovae or stripped envelope supernovae were usually like 20 days or so. So this is much shorter. That means the ejecta mass should be extremely small compared to the normal type 1bcs. And actually this line is a theoretical model that from the ultra stripped supernova, and that matches very well to this observation. And this red line is the spectra, and the black is theoretical model. This is not made to match this particular supernova, but this came just out of the ultra stripped supernova model, and we just overplotted, and that matches very well. So this particular supernova was a good candidate for ultra stripped supernova, and this supernova may have formed the binary neutron star system, which may be merged in some time. So that was about this mass stripping, and we will move on to this merger case, and very strong case or strong suggested case for this neutron star. The supernova which may result from the merger, stellar merger, is this 1987A. This picture you have already seen. So I showed this on the first day as well. So the 1987A, the progenitor was sitting there, and from the single star evolution, you never expect a star to end up there. And another puzzling fact is that it has 10 solar masses of hydrogen-rich envelope and about 6 solar masses of helium core. The radius is very small. So usually if you have like 10 solar masses of hydrogen-rich envelope, then it should expand and they should die at there. But this configuration is really different from what we expect from the single star evolution. And of course, there's many suggested way to make this peculiar configuration at this position in HL diagram, but one major and one strong idea is, yes?
Can you return to the previous ones? And I missed the idea. What is the first peak?
Okay, so this I didn't explain, but so this was kind of cooling. So if the star is really compact, then we don't see the initial cooling as explained in the previous lecture. So you only see kind of the nickel heated part. So this part is heated by nickel. And we observed this early decline, and that was also, of course, kind of not expected from the very compact Wolf-Rayet star explosion. So what it means is we can guess in several ways. So if usually Wolf-Rayet star is so this progenitor is if there's nothing, this is 0.1 solar radius or something like that. So at the initial expansion, this adiabatic cooling makes the initial heat source very small, so you don't expect to see such stuff. So what it means, but we observe them. So what it means is probably the major part of the core was 0.1 solar radius, but there may have been some extended envelope surrounding, which is like 10. I forgot the exact number, but let's say 10 solar radii. So some fluffy thing may be surrounding this progenitor. This may be like circumstellar matter giving you some extra heating source. So that early declining, basically telling you there should have been something fluffy structure surrounding this progenitor, which leads to the early cooling tail. So this explosion was not very simple explosion of the ultra strip progenitor, but this ultra strip progenitor should have done some part of it should have expanded before the explosion to make this early tail. But we don't exactly sure why this happened. But yeah, some theory predicts this ultra strip progenitor should be having some. So there's a shell burning there, and this shell burning, some of them predict this can lead to, just before the explosion, some flappy, some extreme nuclear burning can make this kind of structure. So there's some kind of prediction, but well, that's just the idea, and we don't know exactly how these are formed, but we know there should have been something surrounding this progenitor to explain this early decline. Any other questions? Okay. So this is one example of, so we were talking about 87A, and this is one example of binary stellar evolution, which leads to the 87A, which was located here. So this is one particular case. Is this star was 16 solar mass, and the other star, which we don't see here now, is 7 solar masses. So that's in a binary system. This massive star evolves faster and expands, and then when it expands, this expansion leads to will transfer mass to the other star. So that means as this expands, this star will gain the mass and gets brighter. And in this particular case, in the end, at some moment, so if the separation is large enough, this mass transfer won't lead to merge. But if they are close enough, they may just merge, and then behave as a single star from some moment, and then so that can lead to this kind of structure. So if there's a relatively small core, which basically came from single star evolution, but mass was gained afterwards, after this core was formed, and then this can evolve as after the merger in this kind of structure, and then this particular progenitor were predicted to explode at this location. So there's also these kind of models which can explain this position of 87A progenitor as binary stellar evolution. And also this kind of scenario was suggested to explain this trip. It's hard to see here, but in around the 87A, we see 3 rings. One is here. You may see something here, and also something is there. So there was 3 rings surrounding 87A, which were of course puzzling how to make this structure. And there's a suggestion this kind of merger can lead to of course, it's well, they can make these rings they suggest, and they did some numerical simulation, and if they found they can make these 3 rings, and depending on the angle you see, we can explain these 3 rings which are observed for 87A. And yeah, finally, I will touch on this rotation. And this is important for one important ingredient which may explain this massive binary black hole system which observed in gravitational wave observatories. So, of course, the first gravitational wave, detection, or many of them are coming from these massive black holes, and its formation scenario for this massive binary black hole system is one big discussion currently going on in the stellar evolution community. And the kind of classical way to make such binary black hole is shown in this way. As I said, this massive star, 2 massive stars, and one expands, more massive one expands faster, and that can lead to the mass transfer, and then you can have Wolf-Rayet star, and there may be supernova or not, but this can lead to a black hole formation. And then this should continue, and this second one will gain some mass, and this will expand, and then this again will be high mass X-ray binary, and then this can lead to the common envelope when this second star expands, and then this, if something is inside this envelope, that will lead to mass stripping, and this can also lead the system to get close by, and then there will be a second Wolf-Rayet star. And then this can also lead to a supernova, or maybe they can just cross to black hole, and then you can have binary black hole and then merge. So this is kind of classical picture we have to make a binary black hole system through supernova explosion and so on. But there's another way, another suggested scenario which comes from this binary interaction, which can make the star rotate very rapidly. So if these stars are extremely nearby, so 2 massive stars, actually at first they may be kind of contact binary, but so it should be close enough. Then what can this close binary system do to each other is they can have a strong tidal interaction. So both tidal interaction will make, so of course these stars are rapidly rotating to each other, but because of tidal forces, these stars themselves also need to, tidally locked, and they will also rotate quite rapidly. And what this rapid rotation can do for these stars, as we saw in the first day, they can lead to strong mixing in the star. So what does it mean? So as explained in the first day, this rapid rotation and strong mixing will not lead to the expansion of the star. So in this case, if the separation is sufficiently large, this star will expand, and then there will be some mass exchange. But if this star is extremely rapid rotating, they don't expand, and they will directly goes to the Wolf-Rayet star, as I showed in the first day. What it means is there won't be complicated mass transfer, and this will be just a big single star, a big Wolf-Rayet star, which doesn't expand, and so it doesn't do much mass transfer, and it just collapses as after some time as a Wolf-Rayet star. And this, of course, may lead to gamma ray bursts and so on, but this in the end will just become a black hole. And again, also the other star is not affected by this evolution, And this star again is just rapidly rotating, so this star will not expand, so there will not be common envelope or whatever. This also just goes to Wolf-Rayet star directly without expansion, and then basically you can make two very massive black holes by making this tidal interaction, which leads to the rapid rotation and make the massive binary black hole. So this may be a way to explain this massive black hole binary system, which observed by the gravitational waves. So yeah, this is one example of the predicted Chapman's distribution, and these models are for different colors, shows different metallicity, but there should be some. So these are kind of prediction, and there should be some gap in Chapman's, and there will be a massive Chapman's regime, and why there's this gap will be explained in the next lecture, but this is some prediction. So in this way, you can easily have very massive binary black hole mergers. So that was overview of how the binary system can change the way a star evolve and become as observed as supernovae. And yeah, one obvious way was mass stripping. So more mass can be stripped by the existence of the binary star. If they merge, that can lead to very different configuration of the star from single stellar evolution. And then if these two massive stars are really closely rotating to each other, then this will make these stars to rotate extremely efficiently, and then they will not expand, and they can be directly collapsed to massive black holes. So that was about supernova from binary, and I'm going to move on pair instability supernovae, but if you have any question now about binary, you can ask now, of course later. Okay. Yes.
So binary system is not affected by core of the system.
Could you say it again?
Is binary system affected to core?
So if the binary evolution affects core or not?
Yes.
So if they are not close enough, they will. I mean, of course, it depends on what is your question. If we have a lot of stripping, then the star will be small, so that will make you some smaller core and so on. But like if the core evolution is directly affected by this binary interaction or not, that's I mean, core will evolve like so it won't be affected much. That's the short answer. But if in these cases, of course, these are really affected by the binary stellar evolution, because this is affecting this rapid rotation is making the core big. So it depends on the separation and so on. If they are very close, then this core evolution is strongly affected by the binary system. But if the separation is sufficiently large, then the core evolution itself won't be directly affected by this binary. But of course, there will be many mass stripping and so on. There's many. This core itself is, of course, affected by the binary evolution.
Also, I had some question. So in this scheme with binary evolution, we always have the supernova progenitors with different structure, right? Unlike single stars.
Yes.
So my question is it possible to disentangle these progenitors or channels by studying the nucleosynthesis, explosive nucleosynthesis products, which we extensively discussed yesterday?
So my answer is basically it's hard because this nucleosynthesis result is affected. It's something happening in the core, and that's determined by the mass of the core itself. And of course, many different binary evolution can lead to the different sizes of core. But once the core is determined, what happens as a nucleosynthesis is basically determined by this structure. So if there's a binary system or not, won't affect the nucleosynthesis itself. So of course, the size of core is depending on the stellar, binary evolution or single stellar evolution, but the result of nucleosynthesis itself won't be much affected by. So the core structure itself is not that much affected by the binary system.
So the short answer is that probably apparently no.
Yeah.
Apparently no. We could disentangle.
So if we take the core, like let's say 5 solar mass helium core from single stellar evolution and 5 stellar mass core from binary stellar evolution, and if we do the nucleosynthesis, there won't be much difference. So you cannot tell.
Thank you.
Okay, then let's move on to pair instability supernovae. So this is very different topic now. Let's see. We need to change our mind. So we extensively discussed this diagram on the first day. This is the central density of the stars, and this is central temperature of stars, and we learned that this evolution should go T proportional to rho 1/3. So this is the way it should go. If the mass is low enough, then this will go to this degenerate region, and that will lead to the white dwarf formation. If the star is massive enough, then they will avoid this region, and then eventually it collapses to the core will collapse. And the mass will increase in this way, and as we saw in the ideal gas dominated region, if we see the same density, the higher mass star should have higher temperature, or if the temperature is the same, higher mass star should have lower density. So that's what we also seen on the first day. So as the mass goes up, the line goes up, and then at some moment this stellar trajectory will hit to this region. So in this region, what happens is that photons, which are giving the radiation pressure to support these stars, will be converted to electrons and positrons. So what does it mean? So we suddenly lose this pressure supporting the radiation pressure supporting this star, and you can easily imagine that this will lead to the pressure will be lower, and what in turn happens is this adiabatic index we saw will go down, will go below 4 stars, and that will lead to the instability of this big star, and that will lead to the collapse of this star. So this when stars enters this region, then basically because of the unstable configuration caused by this pair creation, star will just collapse. And when it collapses, then of course temperature gets really high and density gets high, and that will when it reaches this region, this core is composed of carbon and oxygen, mostly oxygen. This oxygen will burn a lot. It suddenly gets this central region gets hotter and higher density. So this will lead to the explosive oxygen burning, and a lot of nuclear energy will be released. And if this burning releases enough energy to unbind the whole star, then this star was originally contracting, but thanks to this nuclear energy, this star can just turn itself to the explosion, and we call such explosion as pair instability supernova. And if the star is too massive, so what happens is that, of course, at first this star will start to contract, and some nuclear energy will be released. But if the mass is too massive, then the nuclear energy released during the collapse won't be large enough to unbind the star. And in that case, this star will just collapse after entering this region, and then it will be a black hole. So that's why there's some mass range of this phenomena to happen. So it's from around 150. So if assuming no mass loss is there, then a star will enter this region from around 150 solar masses, and up to around 250 solar masses. This released energy can unbind the star. So in these mass ranges, there can be this kind of explosion called pair instability supernovae. And above that, let's say 300 solar masses, the nuclear energy won't be enough to unbind the whole star, and this star will just collapse to a black hole. And as I explained, this is caused by the nuclear burning of this inside the star. So it's like it's thermonuclear explosion, and there will be no compact remnant, no neutron stars or black hole will be remained in this after this explosion. So this is one example of how the composition change as this collapse. So this is 240 solar mass case. This is before the collapse. So before entering this, or just before entering this pair unstable region, the most of the mass is like composed of oxygen. So this is something. It's going something this, and now the composition I showed is somewhere there, and then it enters and collapses, and in the end this will change. So at the center many nuclear burning happens, and actually this is after the decay. So this it shows iron 56, but this was originally nickel 56. So there will be many nickel 50 radioactive elements inside, and that can lead to that can make the supernova very bright. So these are another examples. So this is just nickel is they didn't. I mean, this is just after this explosion. So this is 150. So this is the low mass limit of these explosions. So least massive pair instability supernova progenitor. And in those cases, only a small amount of nickel is formed. And of course, originally the density, most of the core was composed of oxygen. But only central part is enough to unbind these relatively low mass stars. So there won't be much nuclear synthesis going on. But of course, some changes are made, and then these stars are unbound. And then this is 250 solar masses. This is almost the highest mass end of this explosion. And then this central part will be strongly affected by this explosion. So original composition is like these at the center, but central oxygen is almost burned and many nickel 56 is made, and then there will be incomplete silicon burning and some other processes happens outwards. So those can be understood based on the Nozomu's lecture in these days. This is already shown in the previous lecture. So what happens? Particular prediction is there's many odd-even effect. There will be a strong odd-even effect, as was explained by Nozomu. So this solid line is what is predicted from the instability supernova nucleosynthesis. These are, I think, collapse normal explosion. So we see many strong difference in these odd-even. Odd and even elements. The difference is large, and this is also again explained by introduced by Nozomu. So there's some stellar candidate that may be explained by this kind of mechanism. Anyway, so this was the result of the chemical nucleosynthesis, but these star will explode, and let's think how they will be observed. So this is helium core mass. So so I showed 150 solar masses is the entire star, and this explosion property is mostly determined by the core of the star. So here. So this end is so this is on helium core masses, but this end corresponds to 150 solar masses, and the other end corresponds to 250 solar masses. So it's different way to show this property. But anyway, so for the lowest end, the explosion energy is, so this is in unit of 10 to the 51 L's. And it's so this is 10 and 5. So it's in the lowest end. It's already like 5 times 10 to 51 L's, and as you go slightly, it's already like 10 to the 52 L's. Let's say if you have 100 solar mass core, which corresponds to roughly like 200 solar masses. Of the star, then the explosion energy will be like 40 times 10 to the 51, so 4 times 10 to the 52 L's. So this explosion energy is much higher than the normal supernova explosion. If you go to the highest end, they can get close to 10, even to the 10 to the 53 L's. And of course, how to make this star bright, it depends. The brightness of this explosion depends on this amount of 56 nickel, which can heat this star. And this is again the same diagram, but for the amount of 56 nickel produced. And this time the axis is here, and this is in solar masses. So as you see around here, which corresponds to 150 solar masses, almost no nickel is made. So almost no nuclear energy can heat this huge star. But remember, there was already a lot kinetic energy or explosion energy is very high. So there will be a lot of thermal energy in the star. So that can of course make explosion bright, as Masaomi explained. But there won't be much nickel 56. And let's say lowest end, it's like 0.1 solar masses or even less in some cases. And then at 100 solar masses or around 200 solar mass progenitor, it gets close to 10-ish. So normal supernovae had let's say 0.1 solar masses of nickel. and this is already around 100 times more than what we usually get. And then highest end, the nickel mass can go like 50 or even more, and this will be extremely bright. So these are some result of calculation, how they look like, and in this case, so 150 solar masses to around 250 solar masses. So these are low mass progenitor, and in this case, progenitor is kind of expanded with supergiant. And so this is like type 2 supernova. So there's, because the radius is large, you can have this adiabatic cooling will be not efficient, and you can use this initial high explosion energy, high thermal energy can make this supernova bright. So this 150 solar mass pair instability supernova explosion, they have almost no nickel, as we saw before. So this is in this end, but explosion energy is very high. So if you have 5 times 10 to the 51 eggs or so, we can still have relatively bright transients. And then as the mass gets higher, you start to have a lot of nickel. So you see, so these if there's no nickel, you basically see some plateau phase, and then this just declines. But you start to see kind of second bump here, and these are basically caused by the heat from the nuclear decay. And as the mass gets higher, this luminosity gets higher. These are spectra, the predicted spectra. And this is hydrogen line, and not much lines are there, because basically this model is hydrogen-free, metal-free model, so we don't see much ion lines and so on. We only see like hydrogen and other. I mean, of course, there's some ions there, but not much. Okay, this was relatively massive. So this was red supergiant progenitor, but when the metal is relatively low, this progenitor may become a blue supergiant, like predicted for like 87A. So 87A was relatively compact progenitor, and that may also happen to these pair instability supernova progenitor. And then if the star is compact, then the initial expansion will be much less. So initial adiabatic cooling will be very efficient. So we don't have much thermal energy remaining as we see in the case of extended progenitor. So at first this declines quickly gets faint, and so if in this case, of course, they don't have, this low mass progenitor doesn't have much nickel, so it just cools down and then decays. I mean, we don't see anything. And then, but this massive progenitor has a lot of nickel, so at first it just declines without the effect of, because of the adiabatic cooling. But from some moment, the large production of heating from the nickel will make this second bump, and then can make them bright. So this light curve is almost like 87A, and it's first it declined very quickly because of the adiabatic cooling, and then we saw the second peak coming from this heating from the radioactive decay. And again, of course, you can these are predicted spectra. So yeah, this is for the red supergiant, this is the blue supergiant progenitor. And as I said, to have this kind of explosion, you need to have a massive core. So you may imagine that if there's a strong mass loss, then you cannot keep this massive star to make this star to enter this region. So of course, in the solar metallicity, you may have like 200 solar mass star at the beginning, but this star will have a lot of mass loss. And then if there's a mass loss, then that means mass will be decreased. And you need to keep this mass up to the point where the central region reach here, so up to the point of oxygen core. So if the mass is lost long before, then central region of the star just goes this way. So they won't enter this region. So you need to keep massive star, and this massive star shouldn't have much mass loss. And of course, if you have a massive star at the beginning, you have huge helium hydrogen-rich envelope, and if there's a mass if there's a mass loss, then this star won't go pair instability supernova. And then the question is, then maybe we don't have hydrogen-free star exploding as pair instability supernova, because to make hydrogen-free stars, you may imagine there should be a lot of mass loss, and then that will lead to this massive core, and that will make this star to avoid the hydrogen, the pair instability supernova region. But this is not the case, and as I'm saying many times, this rapid rotation can make the star like evolve like a single core. So even if the star is initially like very let's say, so if the star is like 100 solar masses, if this star is rapidly rotating, and even if there's no mass loss, this rapidly rotating star will evolve like a single core, and that can lead to like 100 solar mass helium core. So even without mass loss, if there's a rapid rotation, you can have a hydrogen-free massive core which can explode as a pair instability supernova. And this is one example of calculation. This is initial mass, and I think this is metal-free calculation. So if there's no rotation, then this region up to like this is all they assume helium. So this is zero rotation, and this is initial mass, and these are not pair instability supernova. So of course you don't get any explosion as a pair instability supernova in up to, so it should go to 150 or so to get the pair instability supernova. And these red dots are all pair instability supernova explosion. And if let's go to the extreme end, these stars are rotating like 80% of the critical velocity at the beginning, then this rapid rotation can lead to the strong mixing, and even like 70 solar mass star can explode as the pair instability supernova, because thanks to this rapid rotation, this core can make this star can evolve like a single core. They are mostly composed of helium, and so this star will be helium star almost. So then what happens is that this is like big type 1bc supernova, and now there's no hydrogen, and you have just nickel heating, and that's really extremely large amount of helium. Nickel is synthesized, and you can have very bright supernova. So usually type 1bc supernovae, the peak luminosity is around 10 to the 42 ELGS or so, and they become bright in like 20 days or so. So usually type 1bc supernova is like this, or like this, but then they can become like more than 100 times brighter than these type 1bc supernovae. And so as I said, so this is the case of 50 solar mass helium, but as it goes down, some pair instability supernovae doesn't make much nickel, and there will be almost no nickel there. That basically won't make this hydrogen-free p-instability supernova bright, but there can be some thermal energy. So thermal energy, of course, explosion energy is large, so there can be some thermal energy remaining in the core. So that thermal, just from the thermal energy, you can make this p-instability supernova relatively kind of faint transient. So because there's no nickel, they will be much fainter than these other type 1A or type 1BC supernova, but because of the explosion, the high explosion energy, they can still be very faint and long-lasting transient, just thanks to this adiabatic cooling. So, of course, the next question is, so I have explained the observational expected or predicted observational property for p-instability supernovae, and the next question is if they really have observed or not. And there's some supernovae called superluminous supernovae, and they, as the name suggests, these supernovae are really bright. And this is one example. These are data, and they are very bright. So the usual type 1BCs go up to like -18, but this is more than like 100 times brighter than these normal type 1BCs, and these lines are all from the p-instability supernova prediction. So it looks good. This is another example. This is long-lasting, very bright supernovae, and of course, again, there are several p-instability supernova models are overplotted, and they can explain light curve relatively well. And from the light curve perspective, there's several candidates which become as bright as what p-instability supernova models predicts. But serious issues in the superluminous supernova, when we compare with observation and models, appears when we see spectra. And this red one is one example of observed spectra at like 367 days after the peak for one particular example of this bright. So actually this case, so they kept observing and they found this spectra. And this blue line is what the theory predicts. And this is from the peak, and this is from the after the explosion. So they are comparing relatively the same time. And what we see is that the observed spectra is much bluer than what the theory predicts. And what's happening is because of this huge explosion, the explosion making huge amount of nickel. This nickel will decay to cobalt and then eventually to iron. And ions has a lot of absorption in this bluer part of optical wavelengths. So basically theory predicts almost all the light in this bluer part of the spectra will be absorbed, and then everything will be de-emitted in the redder part of the redder part. So basically theory predicts these spectra should be extremely red. But what we observe is we still see many, iron, many photons in the bluer region, which should have been absorbed by iron group elements if there's a huge amount of iron as predicted by p-instability supernova. So these light curve looks good, but the spectra doesn't match well, and we generally don't think they are p-instability supernova. So they are extremely bright, but probably there is other way which are making this supernova extremely bright. And I think one best candidate we have so far for this p-instability supernova is this object, and this was extremely bright type 2 supernova, and the explosion energy is estimated to be more than 10 to the 52 ELS. and nickel mass should be like close to 1 solar masses, and the light curve matches very well. And spectra around this time also, so this is pair instability prediction, and black is what's observed. It's matching well, and at least this phase it matches well. But as we saw here, to really conclude if this is pair instability supernova or not, we need to have very late phase spectra where we start to see into the core, which should have a lot of nickel or iron decayed from the nickel. So we should have get some spectra around this time was essential, but this was very too faint at this phase, and we couldn't observe this object where you can tell if this pair instability is supernova or not. So this was not confirmed, but I think this is the best possible candidate for pair instability supernova if I were asked to name one. And we are almost the end. And yeah, so this is become bright, and you cannot lose a lot of mass to make this kind of explosion. But for the first star, where no ions, no metals are present, you can easily keep this massive core. And also what's interesting is first stars predicted to have a lot of massive stars, which should explode as pair instability supernovae. So this may be happening a lot in the first generation of stars. And so this is predicted light curve at these high redshifts. So like, let's say even if at the redshift of 6, it gets bright enough to observe with next generation telescope. And I am running out of time, but so another final question I have is that, so we were discussing stars which enters this region, but some of them can just touch this region, and then that will not lead to the explosion of entire star, but still some part can be these stars can partly unbound, and some this kind of pulsational behavior is predicted to happen if these stars are not massive enough to enter this pair instability region, but the only touch is there. So then this star can kind of have several pulsation that can also lead to some mass ejection. Not the entire star will be unbound, but some part of the star can be unbound, and some material can be ejected from kind of this behavior, and we call this is kind of behavior pulsational pair instability. Then what's interesting is, so if this pulsation happens very nearby, very soon after the other one, so there can be some mass ejection at first, which leads to some mass ejection, and of course there's some velocity, and immediately after that mass ejection, you can have second ejection, so another pulse can happen, and that may have faster velocity. So this is velocity, and this is mass of distribution from this pulsation. So at first there's a lot of mass is ejected in this particular case because of this pulsation, but so the velocity was small. And then there was a second mass ejection which lead to relatively small amount of mass ejection, but you can have a lot of velocity, and this crashes into this previously ejected material, and then there can be a strong shock wave which can make this system very bright, and these are kind of theoretical prediction, and then these red dots are actually observed supernova, and some supernova may be explained in this kind of way. They are not pair instability supernova, but slightly less massive stars which can lead to this pulsation can explain some bright supernova as well. So this is so this pulsation happens many times, and in the end this star will collapse. So there will be this will be bright like 7 years. So let's say at one time there will be some mass ejection, because of this pulsation. And 7 years later, the next pulse happens, and then this will lead to this bright transient. And then in the end, after several pulsations, this star, after this second pulsation, after several years, this can just collapse. So this will make some bright transients, and this is not pair instability supernova, so this will lead to the massive black hole formation, for example. So that's the end. This just summarizes what I said, and I'm running out of time, so I will just stop here. Thank you very much.
Thank you very much for the talk. Are there any questions? Please.
If constellational interference is occur, after then the supernova is not supernova.
So these are very massive core. So these are in the range where we usually expect the black hole should home. But of course, there will be a collapse, and if the star is rotating rapidly and so on, there could be some mass ejection as well. So maybe like GRB, like supernovae or something. So in principle, some explosion may occur, but this core is too massive to make like a neutrino-driven explosion in a canonical picture.
I missed, but how often do such explosions appear in galaxies like Milky Way?
So it's in the Milky Way, none, because basically, if the Milky Way metallicity is too high to keep, yes. So it depends. So the threshold depends on who to ask, but some people say below 1/3 of solar metallicity may be enough to make this kind of explosion. Then maybe one supernova in 1,000 core collapse supernova may be pair instability supernova if the metallicity is below 1/3 of the solar metallicity. But this calculation, I mean, this really depends on how stars lose mass and so on. So it's hard to tell the fraction. There will be, I mean, we can have some number estimate, but that depends on really, there's many assumptions in there.
Please, can you show the one possible example of the do you have any estimate of the metallicity?
This is relatively low metallicity, yes. I forgot the exact number, but yeah, something like that, yes. Like LMC or something.
Okay. Any other questions? No? Oh, last one.
Did you previous slide?
Previous.
Yes, answer.
This one?
Yes. In this supernova, you say theoretically too much meteor is synthesized.
Yes.
From observation, this supernova, how much iron is?
So we don't know. So of course you can have upper limit for this to explain this spectrum. I don't know the value, and of course from the light curve, if you assume nickel, then you need like 6 solar mass or so. But that's too much to explain the spectra. And I don't know exact value to avoid this. Yeah.
Okay. So let the speaker again.